I gotta go in class.
All right, let's begin. I think this is probably the longest set of slides and the deepest deck I have. And we're going to take a lot of time going through this. I want to go through this slowly. There's a lot of really important ideas. This is the highlight of the class, so I'm going to try to err on the side of boring you guys rather than losing you guys. So we'll see how this goes. I know that's especially a challenge for me. I like to go fast, but sequential importance sampling is the simplest particle filtering algorithm. It's sort of the starting point, the vanilla ice cream, if you will, for particle filters. There are arguably better ways of doing it, although you could say some of the ways of improving it didn't actually result in a lot of improvement, and we'll talk more about that when we look at the different flavors of particle filters. But when you see sequential importance sampling, this is essentially the simple version of a particle filter. Sometimes it's abbreviated as SIS. And let me say, as we get into particle filters, it's helpful to keep in mind what we're trying to do is far harder than what we just talked about with the Monte Carlo integration. We're trying to track a trajectory of a very complicated system in some cases, and a distribution that is multimodal and exists in really high dimensions. And I didn't have to say any of those things other than really high dimensions, and it's enough to make the problem really hard. Whenever you run into a problem where you're trying to do something in high dimensions, it's usually just hard, except in some very special cases, which is what professors like to talk about because they have nice solutions. But the reality is a lot of problems just don't fit that. We want our optimal Bayesian solution. I mean, if it was a perfect world, we would just say, do Bayes. I don't care how many cycles it takes, just do Bayes because it's optimal, you can't beat it, it gives us the posterior, and once we've got the posterior, we can do anything we want. But we can't, and the algorithm that we're going to use relies on Monte Carlo integration, has a lot of different names. These particle filters were created like so many things. People started sort of suggesting different names for it. This occurred with the Synfig-Kalman filter as well, has a few different names. And the most common name is either sequential Monte Carlo methods or particle filters. So if you'll recall from the optimal tracking slides, we talked about two different posterior distributions. One is what I call the marginal, and one is what I call the joint. I call this the joint because this is the PDF of the entire trajectory of the state from time 0 to time n. And keep in mind the state at any given time is itself a vector. So this distribution is very high dimensional. It grows with time. And it's the PDF of entire trajectories. This, what I call the marginal posterior distribution, is only the PDF of the state at time n. It's still a multi-dimensional distribution because the state is a vector in most cases and not just a scalar. So we're in multi-dimensions regardless of which one we look at. But this one doesn't grow with time, and it's easier to work with. It's more manageable. And the key thing that makes particle filters work is we say we're going to estimate the harder one, the joint distribution, as a sum of trajectories, is a good way of looking at this, that are weighted. And each of those trajectories is going to be represented by an impulse function. It's not that we'll ever have to implement that mathematically, but as we go through the derivation and do estimation, it's helpful to think of this representation of the posterior PDF. And in this case, the joint posterior PDF is what we're estimating. And it's actually what you get with particle filters, which is really nice. These are weighted, and so that last plot that we ended with in the previous set of slides, take that and put it in this high dimensional space that grows with time. And that space is really comprised of how the state changes over time in the different paths that the trajectory could take from time 0 up to whatever the current time is. The weights, as we saw before, what we'll end up doing is calculating unnormalized weights, and then we'll normalize them so that they satisfy this constraint. So the weights, the sum of the weights over, in this case, instead of using a capital N, I'm using a little n sub p, where the p is a mnemonic for particles. So this means the number of particles. So if we sum over the number of particles, the sum of all the weights is going to be equal to 1. And so we've got a weighted sum of these high-dimensional impulse functions is what we're using to represent the true posterior joint distribution. One nice thing about this is that your representation of the posterior is now parameterized. We've got a set of parameters, which is the sample trajectories and the weights, and if we know those numbers, then we've got our representation of the PDF. So we've got a finite set of parameters now that really define what the posterior PDF is at any time. And the question that I want to focus on to sort of motivate us to go through this initial set of slides and understand sort of the foundational idea of particle filters is, okay, how do we get those parameters in? Where do we get this set of numbers? Because if we have that set of numbers, then our estimate of the posterior is defined, and the other things we might do with it are relatively straightforward. Calculating an estimate of the state, figuring out how many modes it has, calculating confidence intervals. Once we've got that estimate, those questions are relatively easy. But the hard part is, where do these come from? How do you get those? And make sure that your representation, this is a p hat, we want to make sure that that's a good representation of the joint posterior. There's, as you read some of the papers and chapters that I've recommended for reading for this class to understand particle filters, there's a step that has always confused me. It confused me for a long time when I was first learning about particle filters. And what I saw was that they took the importance density, so instead of P, we've now got a Q, and this is where we're going to draw our sample trajectories from. So we create a sequence of states that it goes through, and we can condition it on y of 0 to n if you like. But I would look in the papers and it said, this is equal to this. And I'd scratch my head and I'd say, no it isn't. I know it isn't, because I know how to do the math, I know how to factor this, I know Bayes' rule, and Bayes' rule doesn't say that this is equal to this. They're different. And it took me a while to figure out what was happening. Let me take a step back and show what two assumptions I made to get from here to here. So the first one is, if you apply Bayes' rule correctly, then what you get, if you factor this, you can say, well, this joint distribution of the importance density for the state from 0 to n can be factored as the conditional, where we've got x of n conditioned on everything else, times the marginal of the trajectory from 0 to n minus 1 conditioned on the same thing, on y of 0 to n. So this is just applying Bayes' rule. And it was my choice to, in this joint, split off x of n from the rest of the trajectory, split off essentially the current state at time n from the past trajectory, the past values of the state from 0 to n minus 1, and make it conditioned on that multiplied by this marginal. And this is just Bayes' rule. That works for any PDF. There's no funny business there. But then when you go to the next step, this next step is a choice. And again, the projector is a little bit wonky, so you can't see it, but this is highlighted in blue. There's a step here where they said this is equal to this, but it's only equal to this because we get to pick Q, and whether we condition Q, our importance density, the way that we generate this trajectory, whether we condition it on the past and present values or only the past values of y is up to us. And so there's a choice made. This isn't math, this is a design decision. In order to be able to make the algorithm eventually recursive, you don't want the state that you're generating to depend on future values of the measurement. And so they change this from n to n minus 1. And then the other design decision that was made is that when we condition x of n, rather than condition it on the entire history of the state and the entire history of measurements that you've observed, let's simplify things to make this easier to code in and to be able to make a recursive algorithm. And let's just condition this on what the state was in the immediate time step before and on what the current measurement value is. So in changing these to this, that was also a design decision. That's not math, that's not Bayes' rule. Those are design decisions. So when you read about this, hopefully that won't trip you up when you see that this is suddenly equal to this, and you're like, it's not the probability theory that I was taught. There were design decisions made there. And the nice thing about this is that there was something important that happened here, and let me take a minute to explain what happened here. If we pick our importance density so that it's in this form, then what that means is when we're creating a trajectory, let's say we've created a trajectory all the way up to time n-1, and we want to advance it one more step. So we've created the state, and we've let it sort of wander around, and then we're like, okay, we want to take one more time step. All we have to do now, because of the way that we've chosen this, is we can take into account where the state is and what the current measurement is, and move that state one time step forward by just making one choice rather than recreating the entire trajectory. So rather than every time you get a new sample, recreating all of the particles, all the trajectories that you're going to synthesize, instead you create your trajectories up to the current time step, and then you append onto them, you add onto them what the next step is for each of the trajectories that you're holding on to, each of the particles, I should call them, rather than trajectory. And so this enables us to do an update, to recursively create these trajectories and move them ahead in time, just like the state space model moves the true state ahead in time. In a way, we just solved half of our problem of how do we create these trajectories. We create them recursively and from an importance density that we choose. And I'll talk more about how to choose it, but fundamentally, we're synthesizing state trajectories, and then we'll take a weighted combination of them to represent the posterior. We've got to figure out what are the weights, and there's math involved in figuring out what the weights are. And there's tricks. We know that the weights, we need the weights to be proportional to the posterior that we're interested in, divided by the importance density that we choose. We pick Q, and we're going to calculate this recursively, but we need to be able to evaluate this and calculate the weights by that ratio. And one of the things we don't want to have to do is every time we go one step forward in time, to have to go through and evaluate this for the entire set of trajectories. Just like we move the state one step ahead, in order as engineers that are doing signal processing and caring about not just the math, but the computational aspects of this, we would like to be able to update our weights in time as well and have a recursive equation for the weights. And so we need to do some kind of factoring of this ratio so that the weight is somehow a function of what the weight was, and we just need to update them somehow. And we got to work out the math to figure that out. So here's that math. And I've simplified a little bit. This really should be the ith weight for the ith particle, where there's a superscript I on all the x's and on all the weights. I just dropped that for the sake of simplifying the notation. There was enough here without adding that in just for the sake of completeness, so I've omitted that. The weight, we know, is going to be equal to this ratio. We want to represent the posterior distribution. And the posterior distribution, if we're going to be generating random trajectories from some importance density, then the weights have got to be the ratio of the posterior we're interested in representing relative to the importance density that we're creating these trajectories from. So that came directly from the Monte Carlo integration slides that we just went through. So that starting point you should be comfortable with. We know from before, from the optimal tracking slides, that the joint posterior distribution, we were able to factor it, and we ended up with an equation I described as beautiful, and this is what it was, where the posterior of the joint at time n is equal to what it was at the previous time step multiplied by the likelihood and the prior divided by this normalizing constant. And so if I drop that normalizing constant, then this is proportional to the likelihood, the prior, and what it was at the previous time step. It's recursive. It's a really nice way of updating the joint posterior. The joint posterior is equal to these two terms times what it was at the previous time sample. And then we made some design decisions on the importance density. We constrained it. We said this can't just be anything. We're going to constrain it, so this has to be of the form that it's equal to this updating importance density for the state at time n, conditioned on the previous state. And actually in the previous slide I had just y of n. In this case I've been more complete, y of 0 to n, but it doesn't matter that much. It's still equal to this by design. We can set it equal to that. Times what the importance density was. And again, we constrained it so that it met this constraint. We decided the importance density that we're going to use will be such that we can update it and in this way. So when we draw new samples, we will draw them only using this information. And then the joint will naturally be the product of those two. So given that information from those two, we substitute those into this equation now. We get that the weights are proportional to. I've dropped this term, so it's just proportional to, and that's enough because we can normalize them. Proportional to all of this stuff, which is just this line divided by that line. And if you write this a little bit differently, and we split off the last term for the numerator and the denominator and write that separately, and if you study that carefully enough, you'll see that's the weight at the previous time sample, which is great, right? Now we've got the recursion that we need. So the weight at time n now is proportional to this thing here, multiplied times what the weight was at the previous time sample. This is the likelihood function. The likelihood function, as we've seen a number of times now, comes directly from our measurement model. From your measurement model, you should be able to figure out what that is. This comes directly from our process model, which in many cases we design and we pick. But you should be able to determine that from your process model. This is just what the weight was, and this is our importance density, which we picked, we designed. So you've got everything you need, except for how do you initialize it, but that's not. So if I make the notation a little bit more complete, because what we're really going to be talking about is a set of trajectories, a large number. And I've seen, we haven't yet talked about how many particles do you need, but usually no fewer than 100. And I've seen simulations I've seen papers that have used like 40,000 for tracking robots through hallways. So that gives you an idea of the range of particles that we're dealing with. But fundamentally, you want as many particles as you can afford computationally. The more particles, the better. But you don't want to be up till 4 o'clock in the morning waiting for your computer to finish generating the results. So there's a practical limitation on how big you can make them. So once again, and I hope I'm not overusing the word beautiful, but once again we end up with this beautiful recursion, in this case for the weights. And again, everything here is known or is something that you should be able to determine. There's not a general equation for getting this from this, but it's usually straightforward, especially if you have additive noise. And likewise for the process model. I mean, it's just not difficult to obtain those, and we'll work through some more examples so you'll see how that works. So, something else magical happened now. We've got our joint now is being the sum of impulses with weights that we now have a nice recursion for calculating. We're done, and we ended up with something that I sort of led you to believe that we wouldn't be able to do, which is that we've got a representation, an efficient representation of the posterior probability that is manageable. When we think about this, we think about this high dimensional thing that's growing in dimension with time to make matters really bad. It's multimodal, it's difficult to handle, we don't have a nice representation of it, and then suddenly I say, oh, you know what, change my mind, we do. It's just weights and the trajectories, and if you've got enough of them, it's a good representation. And it grows linearly in the number of parameters you need. It grows linearly with time. Your trajectory, if you have 500 particles, every time step you need one more of dimension x, and one more weight, which is just a scalar. So it's really manageable in terms of the memory requirements, and the growing dimension suddenly looks like that problem just disappeared. And but then you say, okay, but James, I want to estimate what the state is at time n. Tell me, how do I calculate the state at time n? How do I calculate that estimate? Where does that come from? And it turns out that that's easy when you've got this representation. That's one advantage of working with these particles. Thinking of the PDF as impulses. We've got the joint, but these impulses, an impulse, a multidimensional impulse, or scattered across time, is just equal to the product of the impulses at all the different time steps. And so if we say, well, theoretically, mathematically, if I was a mathematician, I would say, well, if you've got a really good estimate of the joint, just integrate out the state from time 0 to time n minus 1, and that will give you the marginal. Right? If this was the true joint posterior, then you could do that integral mathematically, and it would work out. And the really nice thing about working with the particles is that integrals suddenly become trivial. Integrals become sums. If we substitute our representation of the joint in here and change the order so that rather than doing the integral of the sum, we're doing a sum of integrals. We push that integral in as far as we can. We end up integrating a bunch of impulses. And those impulses just end up having their unit area by definition. And so we end up with our marginal is just equal to the same weights and the sum of impulse functions located at where our states, these particle trajectories, happen to be at time n. So that's our PDF. And from that you can calculate the mean or whatever it is you're interested into. So really you just need to know where are the particles located at the current time and what are my weights at this current time. And from there it suddenly becomes trivial. So there's some magic, and it should almost strike you that we're cheating and that this can't possibly be this good. It can't be this easy to beat the curse of dimensionality. And turn out that it's not, but at least it looks like it does right now. So simplest form of a particle filter is no more than what I've represented on the slide. It's like 3 equations, maybe 2 equations, really. At each time step, and I probably should say even at time step 0, before you have any measurements, you've got to draw from some Q, and there's a way that you've got to initialize this. But nonetheless, at each time step, you draw the next value of each of your particle trajectories. So say you've got 100 particle trajectories. Each one of these is, you can think of as a possible state trajectory the state could go through. And at time n, you simply draw the next value for the ith particle, and you can take into account what the state was at time n minus 1, and I keep switching on this, whether this is also conditioned on the measurement at time n or the entire history of measurements. You can do either. It doesn't matter if this is 0 to n or n, and I apologize for the inconsistencies, but it's really up to you. And usually you only would condition it on what the current measurement is rather than the past values, as I wrote down here inconsistently. But in any case, you move your particles ahead 1 time step, calculate your unnormalized weights. This is your likelihood function, which you can evaluate from your model. This is your prior, which you can evaluate from your model. This is what the weight was. And this is your importance density that you selected. It could be Gaussian, could be uniform, could be anything you want, as long as you can evaluate it point-wise and you can draw samples from it. Those are your only constraints. And then you got to normalize the weights to account for that normalizing factor that we talked about earlier. That's it. Repeat. Go back. Keep going. Whenever you want to generate an estimate, really all you need to know is what your weights are and where your trajectories are located. This is the SIS algorithm. And then the last thing that I'd like to do today is go through an example. And Sam, this is partly for what you were asking about earlier with regards to homework 2 of how do I come up with an example that relates to my research. This is a single-dimensional example that may give you some ideas of what you might do for homework 2. And by the way, the model that you use for homework 2, you're probably going to be using for homework 3 as a particle filter rather than the optimal filter that you did for homework 2. So think carefully about it. It's not just for that homework assignment. You'll probably use the same model on subsequent homework assignments. So this hopefully will provide sort of a template of what you might do for those homework assignments. I made this up. I didn't even know for sure if this was going to work. This is a made-up example that I made up for this class. And the idea is I've got a protractor right here, say, and I can measure the angle theta n. And what I'm doing is I've got a car that's going around a circular racetrack. And as it goes around the circular racetrack, I can point at it and say, you're right there, or you've moved over there. And I can point at it as it goes around. And as it goes around, you know, theta n is going to vary depending on where that car is. Right? I mean, this is not unlike, there are actual sensors that do this, that can measure what the, I guess, the bearing angle is of an object. There are trackers, actually, that do this sort of thing and can track where something is. So we've got theta n, but of course theta n is noisy. Right? It's not, we don't know perfectly. There's some, we know what theta n is with some noise. I know what the diameter of the racetrack is, and I know where I'm located relative to the center of the circular racetrack. I know my car is going around it, and I could have expressed it in units of meters per second or miles per hour, but for our convenience, I put it in units of degrees per second. And so I've got it going around. It's not going very fast. It's going at 2 degrees per second. It takes a while to get around the track. And our sensor is located, you know, I specified what the distance is from here to the center of the track. So that's known. So the geometry of this problem is essentially known. And that's the information that we've got. And I want to design an estimator that tells me where the car is as specified by that angle relative to the track. I want to know, is it here or there, or where is it? And the only information I've got to track it is knowing something about its starting location and the measurements theta n. And I want to point out in this problem, it's going to end up being multimodal because as the car goes around, if I've got noisy measurements, I don't know if theta n is pointing right here, if the car is there or there. Right? I mean, depending, it could be in either location. If I track it well, you know, and I know the history well, then I'll probably be able to distinguish. But that depends on how clean my estimate of theta n is and how good my knowledge of the dynamics of the car going around is. If I knew the car was going around at a constant rate, I don't even need theta n. If I know the starting point, I know its rate, it's fine. But if the car is really jerky, it's got a jerky driver, and you know, I know its average rate, but its average rate and it fluctuates wildly, that creates uncertainty.
Do you know which direction the car is going around?
Yes, it's a positive 2 degrees per second, so it's going around this way. But there's a further ambiguity. If theta was such that it was pointed right here, and I said the car could be there or there, there's another ambiguity. Because I don't know, has the car already made a lap or not? In theta n, I'm representing, I'm integrating as it goes. I'm not treating it as though 360 degrees difference is the same. I kind of want to keep track of how many laps it's made. I want to know the accumulated angle over time. So that makes it even harder. That creates more modes, right? So now if there's a theta n, it's not, it could be here, here. It could be here, here with 0 laps, or 1 laps, or 2 laps, or whatever you like. And I didn't actually know that it was going to be multimodal until I tried it. I was just trying to create a nonlinear problem that was intuitive and interesting and related to something physical. And it ended up being a really nice example with lots of insights. We'll be seeing this example a lot as we go through particle filters and look at other types of trackers. I think this is much nicer than the one that you guys are working through that's in that CAPE paper. That's the knowledge we have. And this is not unlike someone coming to you and saying, here, I've got a tracking problem. This is all I know. And notice what they didn't give you is a model. You know, we need a state space model, and then we've got a lot of math to do before we can build our tracker, and a lot of design decisions. But one of the things that is conveyed by this is that the knowledge that usually you can get when you approach a problem is not the knowledge you need to completely specify the models. There's design decisions that you need to make in how do you represent this knowledge and how do you model, really, to get good tracking performance. So I want to start off with the measurement model. The state space models have 2 components, the measurement model and the process model. And I want to start off with the measurement model. And our goal, our estimation goal, is to estimate what phi n is, essentially where is the car located. And the knowledge that we're given is this other angle that's noisy. So I'm going to represent the noise. This is my first decision, is to represent our uncertainty about theta is additive noise.
How do you, what are you going to use for your winding number or whatever? Isn't that another variable?
Yeah, do you mean for phi?
Well, how many times around? Is that going to just add up? So that would be...
Yeah. So I'm going to represent phi in degrees, but degrees could be more than 360. So when you cross, it just keeps building. So,
Okay.
so it's in there. And I think I'm being a little bit inconsistent. Usually when I represent the normal distribution, what this means is that the random variable, which in this case is additive noise, has a normal distribution. That's what this tilde means. It's not equal to this, but it has a distribution, a PDF, that is a normal distribution with zero mean, and usually that would just be 5, where this is the standard deviation and not the variance. But in this case, I think I was inconsistent with some of my earlier slides where I put in 5 squared, but standard deviation is 5. We were told that we know theta n with an accuracy of roughly plus or minus 5 degrees. And so I said, okay, I'm going to represent that as a standard deviation of 5. You could have said, if your uncertainty is 5 degrees, then let me call that 3 sigma and make it 5/3 rather than 5. Those are more design decisions. And when you're presenting your work and your design, it's up to you to explain that and be prepared to defend it. And it's not that you're making a right choice or wrong choice. It's just a matter of making a choice that you can defend and that is justified and reasoned out, and not just, I didn't know what to do, so I did this. That's not a good response. You have to have a reason. And I thought it was reasonable in this case to say, we know it roughly within plus or minus 5 degrees, so I'm just going to say a standard deviation of 5. I know that that means this is conservative in that I am representing our knowledge of theta as though it's probably rougher than it really is. If it's really plus or minus 5 degrees, you could have argued you should have used a uniform distribution that went from -5 to 5. That arguably would have been a better choice in this case, if that knowledge really was accurate, that it's plus or minus 5. I didn't in this case, but you could have argued that that would be an improvement. And then there is some math to do, and there usually is math to do, where we need to relate theta then to the state. Theta then is not the state, but the state is what we're tracking. And so we've got to go through and do the geometry in this case to figure out how theta then is related to phi of n. And that's got to come from design, from domain knowledge, from knowledge of the problem, knowledge of how what you can measure is related to what you're trying to estimate. So you've got to go through and do this math. And I did some geometry, and I'm sure all of you, being graduate students, would have very little trouble going through and doing the geometry. So I won't walk you through these equations. But at the end of the day, the relationship ends up being that y of n is equal to an arctangent of a ratio of essentially a linear combination of a sine and a cosine of phi. And so there's a pretty nonlinear relationship between yn and phi n. But this is what it is, and this came from the geometry. And the decision to add model or uncertainty about this relationship, about what we measure with v of n, again, was a design decision that I just justified to. This is not atypical. This is common in terms of how you would go about figuring out your measurement model. It usually has to come from very specific knowledge about how your measurements are related to what you're trying to estimate. You've got to figure that out. Where there's more freedom and a lot more judgment and experience is in your process model design. You got to think about this more carefully. I mentioned earlier when we were going through a different example that a very common model is a random walk. This one's different because we have some knowledge about the average rate at which the car is traveling. If we think about phi of n, we know on average phi of n is going to be increasing, and it'll be increasing by a rate of omega. I'm going to assume that we've got a sample rate of 1 sample per second. That should have been specified earlier. But at 1 sample per second, I don't have to multiply by the sampling interval here. But phi of n plus 1, on average, is going to increase from what it was by an amount equal to our omega, which was given to us, times whatever the sampling interval is. And again, I'm just going to assume, for the sake of simplicity, once per second. Maybe I did specify that. Did I specify that? I should have if I didn't. Usually, again, you know that, or you get to pick the sample rate. and deal with the trade-offs between computation and accuracy that comes along with picking a sample rate. We also know that our car is not perfect, our driver is a little bit jerky, and that the rate at which this thing moves is fluctuating as he or she hits the brakes and hits the throttle. And so, once again, I'm going to choose to represent that uncertainty as additive noise. And because we don't have any knowledge about that, I'm going to choose noise that is distributed by Gaussian distribution. You say, James, why do you keep using that normal distribution? There's like 50 distributions that you could choose from that are readily available, that you could draw samples from and calculate the PDFs of. You can do anything you want with them. Why do you keep using the normal distribution? And the answer is the central limit theorem. I don't know if you all are familiar with that. One of you may not be. The central limit theorem briefly says that if your noise, your uncertainty, is due to a combination of roughly equivalent factors, and it's a sum of those linear factors, that the distribution of the sum will become a normal distribution as you accumulate more and more independent factors that generate that uncertainty. This is sort of a lumped uncertainty due to all the different things that, that may affect how phi of n changes from one time sample to the next. And by lumping many independent factors, we know that it's roughly going to be normally distributed. And so in the absence of any other information about that distribution, if you don't know anything else, then the normal distribution is reasonable because of the central limit theorem. So that's why, part of the reason it comes up so frequently. All right, so now we're kind of good to go. We've got our process model. It's in one dimension, just like I want you guys to have for your homework 2 and homework 3 and maybe homework 4. And we've got our measurement model that's given by that equation. I went through and walked you through the design just as I would like you to do. And now I've gone through and I've specified what the different parameters are. And this is important. This is one of the things that a lot of people that publish are not very good at, is collecting all together. They'll go through and they'll tell you what their process model is and their measurement model is, but then they'll leave off a lot of the parameters, like, well, what is R? What is Y0? What is the noise variance? And you have to search and read through the text to find it. And I much prefer that these things are collected together, oral presentation, one slide, in a paper and a table of the parameters that enable you to completely describe your model. And I haven't quite followed that yet here, because I didn't specify what the variance was on the process noise, on W. But so that's an oversight on my part, my bad on that. So in our example, what that means is that we'll start off with some phi sub n, and then let's say we've got 500 particles. For each particle, when I move it ahead in time, all I'm doing is adding omega and drawing a number from a normally distributed random number generator with the same variance as our process model. And I use that to move the particle forward. So I'm using this as the same equation to generate the particle trajectories. It's the most common choice. It's the easiest choice. And it makes the figuring... I should have specified this more clearly, but it's essentially just a weighted average of this term for each value of phi, multiplied by the weights. That's what it works out to be. All right, and now we've got the particle filter. So we've got our process model, and now we want to implement the particle filter, and we've got to choose an importance density. So you could choose whatever you want it to be. I'm going to choose the easiest choice that is what most of you will choose, and is what almost everybody always chooses. There are better choices, but that we'll talk about later. But the easiest choice, and it turns out to not be a very bad choice, is to pick the importance density as your prior. And what that means is that when we are drawing samples and moving our samples ahead in time for these 500 particles, let's say, that each one moves ahead in the same way that would be specified by our easy. So that's the choice I'm going to make. And if I know what phi was at the previous time sample, this is now just a normal distribution, and it's easy. Easy to calculate, easy to draw samples from. Number of particles, I've already talked a little bit about this. It's really a matter of how much patience do you have. It's always more particles the better. In the example I'm going to show you, we're working with 500 particles. in the slides that we're leading up to. And for the estimator of the state, I'm just going to use the mean estimated from our distribution. So that's just a sum of the, a weighted average of the. So in this example, because it's synthetic, I was able to run the simulation once, and this is what the state was. This is how the car moved. You can see it's quite noisy. Our driver is not a very steady driver, and sometimes she goes backwards. She's really not a very good race car driver, but nonetheless, that's what she did. And this is our angle of where she's at on the track, or at least as measured by our other sensor. Not really where she's at, but at least what her bearing is relative to our fixed location outside of the track. And again, one of the things I really like about this is you look at this and you're like, there's no way that you're going to be able to go from this to that to be able to estimate what the state is. Like that's just too hard. Like you can't see anything about the relationship between those two. Like how would you begin to do that? But we've seen exactly how to approach a problem like this. Oh, I screwed up also. I said you got to completely specify things. I did not specify what our knowledge was of the starting location, and I should have. I don't remember how I coded this in, but we'll get a clue in a moment. And I'll look at the code to figure it out. This is the 500 random trajectories that were created. So the car, there's 500 different green trajectories. This is the state, and it's of the ith particle, and there's a separate line for each trajectory that we created, for each particle trajectory of the same thing. The true trajectory in this case went where the red is. So you can see most of the car did something unusual. Here it sort of accelerated and went really fast for a while and ended up in a place different than where almost all the trajectories are. It did something unusual compared to what it would do on average. And that kind of makes this interesting. And then here it just so happened that she kind of went backwards, and so we've got kind of the upper edge of our particles are kind of in our cover where the true state happens to be in this case. You can also see that although I didn't specify it, that there was actually quite a bit of uncertainty about where the starting point was for the state, because there's a big spread there over where the particles landed, where the location could be. This is 500 particles, so that's probably plus or minus 5 sigma, roughly, 4 or 5 sigma, and that covers quite a range. So there was a lot of uncertainty about where the car was starting on the track. It probably would have been more interesting to say, we know exactly the starting location, and then see the cloud of points sort of spread out as it would. Notice also that this cloud of trajectories is increasing. There's very few trajectories that are negative down here by the time you go out this far in time. And if we'd gone out further in time, you would see this continue to widen, but you would also see that on average it's moving up at a rate of 2 degrees per second. The whole cloud is moving up at a rate of 2 degrees per second.
Do you have where would the average, is it a weighted average? It's weighted average, right?
Yeah, and we'll look at that in just a moment. Any questions on this? Normally, you can't plot this. You can in your homework examples, but normally you can't, because the state at any given time is a vector. It's in multi-dimensions, and so you can't look at the whole thing. You can look at different elements of the state. If we were modeling the car dynamics more precisely, where we had the velocity of the car as well as its position, then you could show these separately and show the clouded trajectories separately. But normally you can't look at the whole thing because there's a relationship between those two that wouldn't be captured. So it's unusual to be able to generate this plot. This is a plot of the weights. We've got 500 trajectories. Every trajectory, or particle if you like, has a weight associated with it. And this is the weights on a linear scale. The sum of the weights is equal to 1. And the weights are non-negative, and so all the weights are between 0 and 1. The weights will never be larger than 1 or less than 0. And this shows where the weights are at. It starts off with all the weights being equal. There's 500 particles, so every weight is 1 over 500. And as time goes on, you can see some of the weights get bigger, and then you go along. And then here, something funny happens here. When you get to this time step, suddenly one of the weights is almost equal to 1. It's not exactly equal to 1, it looks like it is, but it isn't. But it's almost equal to 1, and all the other weights then are almost 0. And then you go as time, and suddenly this one goes down, and another one pops up and dominates, and then it goes back down, and this one dominates. And then here there's a switch, where suddenly this weight goes almost to 0, and another weight comes up and takes over, and is almost 1. This shows the same thing, but on a log scale, and shows that as you go forward in time, almost all the weights dive off almost exponentially. Linear on this plot would be exponential decay. And they're dropping off rapidly, and rapidly taking on very small values. Now remember, we're doing a weighted average, and if almost all of your weights are 0, your weighted average is almost a sample of 1. That's not good. That's a problem. And this shows the standard deviation of the weights. So if you take this as a set of numbers and you say, well, what's the standard deviation? It starts off as 0 because they're all equal. And then as time goes on, you get more and more variability. There becomes less equality among your weights. There's one way of thinking about that. And then when you've got one weight that's 1 and all the others are 0, you essentially hit your maximum. This is limited as to how big it can be, because the weights are bounded between 0 and 1. That bounds the standard deviation of weights. But as you see, as you look at the standard deviation of the weights, you want that to be small. You want your weights to be close to uniform. But we can see they become very non-uniform until you hit your maximum. And then again, one weight dominates. And that's a problem. That's a problem. That means when we're taking an average, we're really just including one term in that sum, and we're losing the benefits. We're ending up with previously. Part of the answer is here. When we started off, all 500 particles were contributing equally to our estimate of the average. And it tracked pretty well for a while. It tracked well until about here, and that's when things went badly. And it went badly because suddenly we were relying on just one of those random trajectories, and one alone. We take a weighted average, but all the weights are 0 except for 1, essentially. And that one trajectory then was our estimate. And that's a bad estimate of the mean. If you're estimating a mean, don't average over one sample. You need more than that, right? It's 1 over square root of n. If n is 1, then you've got a lot of error.
Is there any way to have an algorithm when you're figuring your weights out to make sure they don't get too different from each other?
Yeah, and that's exactly where we're headed. That's what we'll be talking about on Wednesday is, okay, something bad happened here, and we kind of understand it, but why did the weights why did so many of them get to be 0? I haven't answered that question yet. And more importantly, what do we do about it? How do we correct for that? And that's what we'll talk about on Wednesday. So we'll answer that shortly after you guys give your presentations. I'm looking forward to. So we'll get there. Okay, good. Thanks, guys. See you guys on Wednesday. Of what the state is. And then this may be the final slide that we go over today. Let me explain what's here. We did a lecture on optimal Bayesian recursions that works in low-dimensional models. I applied that here, and that's what I used to estimate what the true posterior PDF is. This is not the estimate from the particle filter. This is the estimate from the optimal tracking. And so the pink region is the true 95th percentile. We can see something interesting happening here where we've got a bifurcation, we've got an uncertainty about where the car is. And then as we move ahead, we get some information that tells us, oh, nope, it's not down there. And then as we move ahead, it stays up here. That's interesting. And then as we move along, here's another bifurcation where we don't know, is the car down here or is it above? And as we move forward, those two come together, and then suddenly we know where it is again. And there's another kind of bifurcation here, and then that one ends, and now we've got new information now, we know where the car is, and so forth. So there's cool stuff happening there. But that knowledge is coming from the optimal filter, which we're not going to be able to apply in high dimensions. So it's just here to give us sort of ground truth on what's going on. the true state is shown by red. And keep in mind, the posterior and the red don't have to match up. The true state could be in an unusual place. And even if you've got the optimal estimator, it could be wrong. Right? The state is random, and it could be someplace different than where it usually would be, given the set of measurements that you've observed. And we see an example of that here. The true state, we saw that rapid acceleration that was highly unusual. And here, up here, she's out of the 95% confidence interval even, which we expect to happen 5% of the time. And down here, she's in an unusual place also. But our estimator is still good, especially on average. I mean, we still have, with the shaded region, you can't beat the knowledge given by the shaded region. It comes from that optimal estimate of the posterior. Even for the measurements we've observed, it was unusual that she would be there. And then we've got the particle mean. And I said, particle filters are great. It looks like they beat the curve's dimensionality. And you look at how this thing starts off, and it looks great. It's right where you want this to be is if you've got a single mode, essentially right in the middle of that mode. The posterior in this case is roughly Gaussian, and so the mean should be roughly in the middle. And you can see it starts off great. It's right in the middle, and it's tracking really well. It's right where it should be. And we get up to here, and then things start to fall apart. It went down when the true state went up. And the true mean, when you had this bifurcation, the mean ended up in between the two modes. And then when we got this new information, the true mean snapped up here. And actually, nicely, the particle filter mean did too. But then it starts to drop off. It ends up in a very improbable place. And then it just goes crazy. And it's not at all where it should be. And it jumps around. It's kind of okay. And then it comes down here. And it should be right tracking perfectly what the true mean of the posterior is, where the blue is. The blue and the red should be in exactly the same place. And if we had enough particles, they would be. But we had 500 particles in a one-dimensional problem, and they weren't. And you say, well, what happened? Why did it work so well at first? We start off here, and it's good. It's doing really well initially, and then it gets bad, and we end up with it being in crazy places where it shouldn't be. I wish I hadn't rotated that. And the